Hello everyone and welcome to another video. Today I'd like to continue our discussion on building a nonlinear 6 degree of freedom aircraft simulator. So if you recall, in our previous video we discussed the research civil aircraft model, also known as the RCAM model. We built up the equations/models describing the aerodynamics, propulsion, gravity, etc. that comprise the equations of motion for this aircraft. This laid the theoretical foundation for the aircraft model, and now we're actually ready to spend that mathematical capital and implement in software to generate an honest-to-goodness flight simulator. Since we spent almost 2 hours in the previous discussion going over the model in detail, we're going to move at a somewhat accelerated pace today, since all we're really doing is translating these equations into lines of code. Obviously, if you haven't seen that video first, you might feel more confused than a chameleon in a bag full of Skittles, so please make sure you watch the videos in order. Assuming that you've watched the previous video and you're comfortable with the contents, why don't we jump over to the whiteboard and get started. All right, so I've rewritten our flat Earth equations of motion for a rigid 6 degree of freedom object, and here they are, right? And then last video we discussed what made these equations specific to the RCAM model, namely it was how the external forces come in, and we saw that they were a function of gravity, the propulsion slash engines, and the aerodynamics, and also how the external moments were specific to our particular aircraft. Again, the engine slash propulsion cause a moment, as well as the aerodynamics cause a moment, as well as the last couple terms are the mass was aircraft specific, as well as the inertia matrix and its inverse here. Okay, so that was the last video. So now what we need to do is we need to go ahead and figure out how to implement all of this in Matlab. Remember, we spent 2 hours discussing how to build up all of these functions and what the relationships between the aerodynamics and the state vector were and all that kind of stuff. Now we're in the position to package this up into a Matlab function. So let's go ahead and do that. The whole purpose of all these complex 9 differential equations is to basically calculate the state derivative dot, right? So again, remember, here's our state vector, right? It said it was u, v, w, p, q, r, phi, theta, psi. Well, all of these relationships gives you u dot, v dot, w dot, p dot, q dot, r dot, phi dot, theta dot, psi dot, right? So the left-hand side of this, what we want is, coming out of this is going to be x dot, right? Okay, and if you think about this long enough, we now have to figure out what is necessary to compute this. Basically, we want to come up with a function which is basically our RCAM model, right? Where its sole job in life is to compute the state dot. Well, what is it going to need to do that? Well, obviously, if you look at these equations, we see that, okay, there's obviously you're going to need constants. Right, we remember that things like the aerodynamic, the tables, it had a bunch of different slopes, an angle of attack where it switches from linear to nonlinear. There are all these other constants associated with it, so we can bake that in here. But then there were things like here, this term right here, that was just UVW. This term right here, this is x456, right? So we see that the state vector is also needed. So I need to know the state vector at the current time in order to compute the state vector dot, okay? The other thing that we need, it might not seem explicitly written here, but if you remember back in our discussion, we said things like the aerodynamic forces, right? If you were to sit here and adjust the aileron, the tail, or the rudder, that's going to affect like the lift, drag, or the side force, and it is also going to affect the moment here. Right? And here, like these other two, if you look at these two control surfaces, right, the throttles, if you crank up these throttles, it's definitely going to change this term right here, right? This is the net force due to propulsion effects, and here's the net moment. So that's going to weasel its way in there. So long story short, you also need the current control, right? So if I have the state vector at a given time, I have the control vector at a given time, I have all these constants, I should be able to now package all this up into a Matlab function and have it compute x dot. That's our game plan. So what I want to do is go ahead and let's go over to Matlab and basically build this function. Let's call it actually, how about rcam underscore model dot m, right? So this thing's, like I said, its sole job in life, it is a function where you pass in the state vector and the control vector, and it will then compute x dot, okay? And the way we're going to get that is we're going to basically go through that exact same 10 steps that we derived in the previous video, where we built up things like the dimensionless aerodynamic coefficient in FS, and then we did all the rotations and yada, yada, yada. In fact, I mean, just to refresh your memory here, maybe I'll flash up on the board right here. Here were the 10 steps that we talked about in painful detail last time. Now all we have to do is translate those equations into actual lines of code. So if that sounds good, let's jump over to Matlab and do that. All right, so we've just got a blank Matlab script, so let's go ahead and define what this function should look like. So we said this thing was going to be called RCAM model, and the interface was, again, we pass in a 9-element state vector x, a 5-element control vector u, and this thing kicks out a 9-element vector, which is just x dot. So that's pretty good. Let's go ahead and save this as, yep, RCAM model.m. There we go. And now we can just start walking through our 10 steps. And actually, before we do that, maybe what we should do is let's have 2 small sections to start where we are going to do a couple of extra things. Namely, and in order to save time, I'm not going to type everything in. I've actually got this prepared off screen, so I'll just copy and paste in the first thing I want to do. So the first thing we're going to do is it might be nice if we break out all the states x1 through 9 into individual variables called x1 through 9, just so that we can get away without not having to do all this indexing down the road. And again, we remind ourselves here that this is the state vector. It's u, v, w, p, q, r, phi, theta, psi, right, in that specific order. Similarly for u. Okay? That's the first thing that we want to do. The next thing that I want to define in our function is all of those constants. There were a ton of constants with the RCAM model. So again, I'm going to grab from off screen and I will just go ahead and paste in the appropriate values. Let's scroll up to the top and maybe just talk through these. So, here, the first thing, the mass of the aircraft, the nominal aircraft is 120 kilograms. You might be really tempted to define the inertia matrix here, and you totally can, but I'm going to defer that as it's going to be relevant to our discussion a little bit later. So tell you what, instead of defining that 3x3 inertia matrix right here, you can go ahead and we're going to do this somewhere else. All right, let's keep going. All these other parameters like C bar, this mean aerodynamic chord, all of this other stuff, everything is pretty standard. The only thing that I will maybe call out is this ZCG value. The RCAM document has a little bit of an inconsistency. In fact, I'll flash it up right here. Depending on if you're looking at table 2.4 or table 2.5, you might see different nominal values of what the RCAM document suggests you should use. I'm going to go with this 0.1 C bar value. As it seems a little bit more correct, I guess, and there's less typos associated with this value. So anyway, other than that, there's nothing very fancy about this section, right? All we're doing here is defining all of these constants, like where are the engines located, right? These are these application points of thrust of engine 1 and engine 2. And then all of our other constants. Here's our constantly assumed air density, remember? So we talked about this in the previous video. We're going to assume that the air density changes with altitude are negligible, and we're just going to hold it constant at the sea level value. And then again, here's all of these other numbers. The only thing that maybe is also relevant to point out is, again, remember we talked about it in the last video, but the A0 number in the RCAM document yields a discontinuous lift CL alpha slope. So we're going to use this slightly modified value. Okay. So with those two kind of pre-sections done, we can really just start jumping into the 10 steps that we talked about earlier. So the first thing that we needed was control saturations. So again, to save time, let me copy this from off screen and I'm just going to paste it in here and then we'll walk our way through it. So, section 1, right? Control limits and saturation. So remember, the RCAM document said that the ailerons here, which was U1, can only go between minus 25 and 25 degrees. The tail can go negative 25 to positive 10. The rudder can go from minus 30 to 30. And then the engines, again, this we're going to revisit this in a little bit, but right now we said that the engines, you actually can't turn them off, right? Here's the minimum thrust they provide, and here's the maximum thrust. Or, excuse me, not the actual thrust, but this is the minimum deflection, the control, minimum throttle setting, and the maximum throttle setting for engines 4 and 5, okay? So then, once we've defined the limits, the upper and lower limits, the next thing I'm going to do in this next section is, really, I'm just going to run each one of the control elements through basically an if check to saturate to see if we're outside of those bounds. So, for example, right, if the aileron is deflected beyond, or at least the passed in value, right? This is the value that is passed into the function. If that is above the maximum value, we're actually just going to saturate that value at the upper limit. If it's below the minimum value, we'll saturate it at the lower limit. So actually, after line 81, we guarantee that this value U1 is within the desired control, or within the specified control limits for that channel. And then we do the same thing for channel 2, 3, 4, and finally for control number 5. Okay, so that's section number 1. What was our next section? I think the next section was all of those intermediate variables that we discussed. Okay, so again, let me just paste it in so we can go a little bit quicker here. So here's the intermediate variables. Again, we talked all about what these were in the previous lecture, so I'm not even going to talk too much about them, other than, again, call out maybe some gotcha moments. Again, notice we use a tan 2 for the angle of attack. We do not use a multi-quadrant inverse sine. So here, you may have to think about this a little bit, but we're going to hope that beta is never in ridiculous ranges. So this is probably okay. Dynamic pressure, and then a couple of these terms, which are basically just portions of the state vector stacked up. Okay. There we go. That's done with number 3. Okay, section 4 was the big one, and I think we spent the most time in the lecture last time talking about that, but it's actually not a ton of actual code. So if we paste this in, we can talk about section 3. So section 3, if you notice, again, all we're doing is implementing all of those equations we talked about earlier. So here is our nonlinear lift curve, where it is linear until the angle of attack alpha, which we have just defined here in line 112. If that is above this I think it was 14.5 degrees. If it's above that, we will now use the this polynomial version and to basically model positive stall, right? Okay, that's great. And then we just go ahead and do the same thing for our tail, right? We implement the CL of the tail equations, and then we add them together. And since the RCAM designers were nice and already took into account the difference in normalizing areas, we can just directly add them. And then again, we do the total drag force here. And again, remember we had this discussion, this is really drag and the stability. In fact, the lift, drag, and side force, all of these are in the stability axis, right? So, there we go. We calculate all those dimensionless coefficients, and then the next thing that we can do is move on to step 4, and we are going to now just go ahead and dimensionalize those. So, again, I'll copy from my prepared script off screen, and here we go. We will stack up all of the coefficients, right? And we will put the appropriate sign and put them in the appropriate, either the force in the x direction, the y direction, and the z direction here. And we will then scale them all up. So what I've done here is just created the dimensional aerodynamic force in the stability axis. And then all we need to do is calculate our rotation matrix here, right, which rotates from the stability axis to the body, from the stability frame to the body frame, and then I can go ahead and apply that rotation matrix to rotate the aerodynamic force from the stability axis to the body axis. Great. Okay, so moving on, let's move on to step number 5. Step number 5 was, I believe, getting the dimensionless aerodynamic moment coefficients about the aerodynamic center in FB. That's a lot to say, right? Okay, so here we go, step 5. So again, we are just implementing the equations that we discussed in our last video. So you remember that eta vector was sort of our static stability that we discussed. So I've just broken it up into a couple of intermediate variables. But again, you guys are all good at Matlab at this point. This is just making that happen. I'm going to define that 3x3 matrix, which we kind of used that abusive notation and called it DCM dx, but really it's the it's how the moments change with respect to a state, namely x4, 4, 5, and 6, right? That's what this matrix measured. And then finally, here was our quote-unquote control authority or control effectiveness sort of matrix. Again, this one was going to be multiplied with the controls. So as you can see right here, controls 1, 2, and 3. So again, this is just implementing those equations that we talked about in detail last lecture, so I'm just going to gloss over them and just show the code that we need to get them entered in. Okay, that was the tricky part in terms of defining the code, because now we've got the dimensionless aerodynamic moment about the aerodynamic center in the body frame. So step 6 is really just scaling, dimensionalizing that dimensionless coefficient. And again, maybe we will call out that the thing that's nice about this is the RCAM designers, again, decided to use the exact same normalizing length for all of the moments. So really, yeah, you don't really have to do anything here. You can just go and normalize all of them by the exact same normalizing area and the exact same normalizing length to get the actual moment here. So this is the moment in terms of Newton meters about the aerodynamic center expressed in FB, right? And expressed in the body frame. All right, so moving on to step 7. Step 7 is just performing the moment transfer to move these moments from the aerodynamic center to the center of gravity. And again, maybe we'll just call out that I believe the RCAM document has a sign error in their expression. So we are going to use our derived expression to do this moment transfer. And maybe I'll also call out that Matlab has a nice cross function that you can use to do the cross product. So, nothing much to say about this since we already spoke quite a bit about this in our previous video. So, let's move on to step number 8, which again, I prepared off screen. I'll just paste in the code and we'll talk about it. So, here we go. Here are the engine forces. And again, maybe the thing to call out is that the force produced by engine 1 and 2, right, we see that they are directly related to the input throttle setting U4 and U5. Now remember, way up at the very top, we had saturated this to a minimum and a maximum value, and the thing that was interesting about this is the minimum value is above 0. So we see that in this current implementation of the RCAM model, there's no way to stop the forces generated by these two engines, right? They're always going to be providing some minimal amount of thrust. And again, I'll call that out because we'll come back to that in a little bit. But otherwise, assuming that is all set, we can go ahead and calculate the actual force that those two engines are producing as a vector, add them together to get the total propulsive force expressed in the body frame, and then use our cross product again along with the difference between the position vector of the application point of thrust and the CG of the aircraft, and we'll get the moments that those two engines produce about the body, or about the center of gravity expressed in the body frame. Okay, so there we go. That was step 8. Now, step 9, which was our gravity effects, was really easy. Again, we talked about this already, so there's no need to discuss. Here, what else? Let's keep going. Our last step now, this is where it gets sort of interesting. I'll go ahead and copy it from off screen and paste it on here to take a look. So let's go ahead and chat about this. So the first thing you note, and maybe we'll call this out now, is that right here is where I define the inertia matrix. Again, this is a matter of personal preference. You could have defined this inertia matrix way up at the top where we were defining all the other constants like mass, whatnot. The only reason I did it down here because I think there's a little trick that's worth mentioning, and I think it helps visualize why we need this trick. So if you remember down here on line 239, this is basically implementing Newton's second law of rotation for our flat Earth equations of motion, right? And notice that we need the inertia matrix, and we also need its inverse of the inertia matrix, if you notice. Now, what I've done here on line 229 here is I've actually gone ahead and offline, I've computed the inverse of this constant matrix and hard-coded it in here, right? You could alternatively say INV IB gets inverse of IB, right? This is another way to do this, right? This is another way to implement line 229 where we're just getting the inverse. Now, the only reason I'm calling this out right now is this is kind of a stupid thing to do, right? Because the inertia matrix is constant, right? It's never ever changing. So if we were going to call this RCAM model.m function like thousands of times, say within a simulation, why would you waste time asking Matlab to compute a 3x3 inverse every single time, and it's just going to give you the exact same answer every single time? So instead, to save that computational time, instead of asking Matlab to compute the inverse, I'm just going to compute it offline one time and then hard code it in here to save me some effort. So the other thing to maybe note is I don't think we discussed the structure of the inertia matrix in our previous video, and now might be a good time to do so. If you notice here, this matrix is symmetrical, and there are a lot of off-diagonal zero terms. This is consistent for an inertia matrix of a vehicle or any object which is symmetric about the xz body plane, which it totally is for an aircraft, or at least for most aircraft, right? If you split an aircraft right down the center, the starboard side looks exactly like the port side. It's just a mirror image reflection. The other thing that maybe we'll call out right now is that the RCAM document, again, seems to have a bit of an inconsistency. If you look at how they define the inertia matrix on page 12 versus how they define the inertia matrix on page 91, you'll see that there's an inconsistency in the thousandths and 10,000ths place of one of these entries. And furthermore, there's a further typo in the entry that has an inconsistency. It is the IXZ entry, and you see there's a slight typo there. So due to those two typos on page 91, I'm going with the version that's on page 12 here, which is what we've implemented. Okay, so enough talking about the inertia matrix. Again, the way the inertia matrix is used is right down here on line 239, where we basically implement Newton's second law to calculate x4, 5, and 6 dot. Similarly, on line 235, we have Newton's second law of translation, which gets us x1, 2, and 3 dot. So, lastly, down here on line 246, we are implementing Euler's kinematical equations, which again, we had a previous video discussing Euler's kinematical equations, and this is just our choice here to make our lives easier and make the code easier. We could have had a whole other section implementing Poisson's kinematical equations or the Quaternion kinematical equations, but to make our life easy for this first cut, let's go ahead and use Euler's kinematical equations. So at this point, we have, again, this is x1, 2, 3 dot. This is a 3 by 1 vector. This is x4, 5, 6 dot, which is again a 3 by 1 vector. And then finally, this is x7, 8, 9 dot, which is another 3 by 1 vector. So all we need to do is stack them one on top of each other to get this 9 by 1 vector, which is the state derivative dot. So that's all there is to it. If we come now up to the very top, we see that you pass in the current state vector and the current control vector, and in just 250 lines of code, we can compute the state derivative dot of this full nonlinear 6 degree of freedom, twin engine, 120 kilogram commercial transport jet. So let's go ahead and save this. And we've got the RCAM underscore model.m function, which gives us this functionality. So what do we want to do with this now?
All right, so we've fully defined this Matlab function, right, RCAM model.m, but this is not actually the entire aircraft, right? Because if you look at this right now, x dot and x, these two signals are not related the way that we've drawn this, right? And we know that these two have to be related, right? They're related through one integration. So in other words, if I go ahead and now stick an integrator, right, here, what this is going to now output is x, right? You integrate x dot, you get x. So in order to make this consistent, I need to actually wrap this back like such, right? So now this overall system has the control surfaces coming in. It's going to calculate the state derivative dots. It's then going to integrate it and feed that back and use that for the same for the calculation at the next time step, right? So this entire picture, right? This block diagram is consistent, and this is our aircraft. So if I were to just outline this maybe in blue, like such. And maybe what I'll do is let me pull this vector a little bit further out, right? So now, this thing in blue is the non-linear 6 degree of freedom aircraft simulation, right? Because what comes in here is on the left side, you have the pilot inputting the whatever the aileron, the tail, the rudder, the throttles, whatever those are, and then all this integration is going to occur, and it's going to basically compute the state, right, of the vehicle, how fast it's going, its angular velocities, and its Euler angles, and that will come out on the far side. So this right here is our model of our aircraft, right? This is our
RCAM aircraft. So what we need to do is let's go ahead and see if we can integrate this into Matlab Simulink and build a block which implements this in Simulink.
All right, so let's go ahead and fire up Simulink and start ourselves a blank model. And the first thing we want to do with this model is let's go ahead and save this in the same directory as the RCAM model.m file. So maybe let's call this RCAM simulation. Hit save. Okay, and we can just now start building the diagram that we had on the board. So I'm going to start with the integrator. That's what I like to do. And what's coming into the integrator is our signal x dot, which maybe let's label this explicitly. This should be our 9x1 vector. We integrate that, and coming out of this should be x, which is also a 9x1 vector. The last thing that we should maybe talk about before we leave the integrator is the initial condition here. Let's just set this to a variable called x0, and I will come over to Matlab, and let's start ourselves a script whose sole job in life it is to initialize constants. Initialize constants for the RCAM simulation, right? So let's start off with our good old friend clear CLC close all, and then let's go ahead and define constants here in this first cell. So x0 is going to be, again, I've got this prepared off screen so you don't have to watch me typing things in. This is the initial condition. So remember, this is U, V, W, P, Q, R, phi, theta, psi. So we're going with a U velocity of about 85 meters a second, which is about 165 knots, and we're pitched up at about 5.7 degrees. So this is the initial condition. Okay, coming back to the Simulink model, we've got that defined. The other thing that we need is probably our control vector. So we need to know what control surface deflections are we trying to fly at. So I'm going to come over on the far left, and let's just set them to be a constant for now. So this constant, let's set this just again to another variable of, let's just call it u, and we'll come back to our script where we're initializing constants, and we'll pick our initial u. So the initial u that I'd like to use is this. So remember, this is basically saying 0 ailerons. The tail is actually down at about negative 5.7 degrees. There's 0 rudder, and then both controls for the throttle they're set symmetrically at 0.08. And if you recall earlier, the limitations on the throttle, the minimum value was 0.5 times pi over 180, which evaluates to about 0.009. So we're not saturating the controls in any of the channels, and both of these throttles again are applied symmetrically. So both engines have the exact same throttle setting. Okay, great. So we've got that set up. So coming out of this block is going to be the signal u, which again is a 5x1 vector. So at this point, we basically have everything we need. If we branch off this signal x and bring it back, you'll see that now what I need right here is I need to be able to call the RCAM model.m to calculate x dot, right? So that's what we need. There's a couple of ways you can do this. One of them is you come here to your Simulink library browser, come here to user-defined functions, and grab this Matlab function and drag and drop them into the model. And if you double-click on that, you'll see what this Matlab function block allows you to do is basically write Matlab code and input that. So if you come over here to the RCAM model.m file, what you can do is Control-A, select everything, copy it, and come back to the Matlab function block, and paste all of that code inside. And now if you save this and you come back to the Simulink model, you'll see what that does is it basically allows us to perform that calculation. This is the same calculation that RCAM_model.m was making. So one way to skin this cat is you can just drop this in right like this. So let me hook everything up just for completeness, and then X comes over here. Whoops, let's bring that up. Okay, like that. Oops, sorry. There, like that. Let's hit save. So this is one way you can do this. This should work right now. The only problem, though, the thing that I don't like about this is if you think about this long enough, unfortunately right now we have two versions of the code running around. So there's this version right here. So this one on the right, this is the code that is inside the Matlab function block, and it's completely separate from the code that's in RCAM_model.m. Both of them have the same contents, but they're different instances. For those of you who are software developers, I think this is probably throwing up a bunch of red flags in your head because I don't know about you, but I detest having the same code copied in two separate locations, right? It makes maintainability a nightmare. Like, for example,
what if we came here in the RCAM underscore model.m and somebody said, you know what, the vehicle doesn't weigh 120,000 kilograms. That's not the mass. It's actually 110. So you come here in RCAM underscore model.m and you update the mass to be the appropriate value and you hit save, and oh, whoopsie daisy, look at this. It's not automatically updated in the Simulink diagram. So basically, this Simulink model is now inaccurate. It's not reflecting the current value that you want. So again, this is not a great idea to have two instances of the same code floating around. So instead, I really don't want to use this block. So let's go and close this, switch the mass back to the nominal value, and come back to the Simulink model and delete this. So really, I don't want to use this. Instead, what I want to do is I really want to have Matlab call this particular RCAM underscore model.m function and use it to calculate the state derivatives rather than copying it into a Matlab function block. So the way we're going to do that is let's again come to here to user defined functions and grab an interpreted Matlab function and drag and drop. Now, if you look at the block parameters for an interpreted Matlab function, you see what it allows you to do is it allows you to call any Matlab function like sine, cosine, tangent, whatever, or check this out, you can also call user-defined functions, right? As long as it's on the Matlab path and Matlab knows where this function is, it can call it. So what we can say right here is we can say, all right, I want you to call RCAM underscore model. And then, here's the one issue. I need to pass in parameters. So, the thing that makes this interesting is if you look at this, the interpreted Matlab function only has one input nubbin coming in. I need to pass information about both the state and the control vector to RCAM model.m. Right? So, the way to get around this, and the way to do this, this is an interesting little trick, is let's go ahead and grab ourselves a mux, or a multiplexer, okay? This multiplexer, what I'm going to do is I'm going to now use it to stack the state vector on top of the control vector like this, okay? So maybe let's double-click this to get the label over here so we can see what's going on. So you've got X on top and U on the bottom. So coming out of this thing is actually this giant mega vector called XU, which is now a 14 by 1 vector, right? So what we can do now is if I hook this up like this, okay, this is, we're almost there. I need to open this up and take a gander at the input parameters. Now, here's where we have a slight naming collision. If you're reading the help documentation on this interpreted Matlab function, notice here that within the scope of the interpreted Matlab function, U right here, if I type in the symbol U, lowercase u, this refers to the inputs to the block, or the input signal coming into this interpreted Matlab function block, which we see in our case, it's actually a 14 by 1 element vector. Now, the problem here is our function, RCAM underscore model, if you look at it up here in the Matlab script, right, it expects two separate inputs. It wants a 9 element vector first, followed by a 5 element vector. So we have to input two separate vectors. So the way to get that to happen here in the block parameters of the interpreted Matlab function is you say U1 to 9 and then comma U10 to 14. So hopefully if you stare at this long enough, it's going to make sense, right? What this does is it says, okay, take the first 9 elements of the 14 element input, which in our case is the states, and pass that as the first argument to RCAM model. Then take inputs 10 through 14, which you see right here is actually the control vector U, and pass that into RCAM model as the second input. So again, I think I'm rambling at this point. I think hopefully this makes sense if you look at how these are lined up, right? Okay, so with that being said, I'm going to hit apply. Okay. And I think we're ready to go. So let me save the RCAM simulation. Let's come back here to our initialization script. I guess we should have saved this, I guess. Let's save this here in the same directory and call this thing like initialize constants. Okay. And maybe let's do one more constant. Let's say TF, the final simulation time. Let's make this like 60 seconds. And then I'll come back to the Simulink model and change this. Instead of 10 seconds, let's make this TF. Okay, so we simulate for 60 seconds. Okay, what else should we probably do? Let's save some of the data. So for example, let's save the state and the control vector. So what I'm going to do is let's come here to our syncs, and let's get a to workspace block and drop this in here, and I'm going to call this thing SimX, because that's the simulated version of the state vector. And then over here, I'll hook this up, call this thing SimU. Okay, and we'll use a time series, and I'll go ahead and hit save. And now if I come over to my initialization script, I can go ahead and now run the model from the script using the sim command. So what we need to do is we need to say sim, what did we call that thing? What was the name of our simulation? Oh, here, it was called RCAM simulation.slx. There we go. And if I now run this script, it should define the constants, run the model, and generate the data. And there we go. We've got SimX and SimU created. Maybe now's a good time to maybe mention I'm running Matlab 2018b. I think if you're on a newer version of like Matlab 2019 or 2020 or anything newer, these variables may be saved in a different data structure. I believe like an out data structure. So if you're on a newer version of Simulink, you may need to modify the code slightly, but I'll assume you're able to do that. So now that we've got the data, what we can do is let's go ahead and plot the results. So let's go ahead and, again, to save the time, I'm just going to go ahead and copy and paste from off screen. So again, all this is doing is just unpacking all of the data from these two time series that were created. And then let's go ahead and plot all of this. Again, to save ourselves time, I've got this all prepared. So, for example, I'll plot the first control input. This should be the aileron. And then let's go ahead and do the same thing for all the other control inputs on the same figure. So here we go. So here's plotting aileron, tail, rudder, control 1, control 2. And then let's also plot, how about the states? Because that's what's more interesting. So if we go ahead and do that, again, I've got all this prepared off screen so that you're not going to have to just watch me typing in a whole bunch of stuff. I'll paste this in and we'll, whoops, where did it go? Okay, so we'll take a look at this. So again, yeah, so in the subplot, I've got the first three as being X, X1, 2, 3, which are UVW, and then PQR, and then phi, theta, psi. Okay, so if we run this, this should now do everything. It should initialize the model, run the model, and then plot up the results. So here we go. Let's take a look. Whoops, what happened here? Oops, that should be a 5. Sorry, hold on. Let me update that. And that should be U5. Sorry. Okay, let me run this again. I had a small little bug there. Okay, it's running, and let's take a look. So here's the first one. Here's all the controls. As expected, since we just had a bunch of constants, right? You remember, look here. This is just a bunch of constants. You can see that, okay, no aileron. We had the tail at the right spot. We had no rudder, and we had a constant throttle on both. Now, let's see what happens. What does the vehicle do? Now, let's pull this over and take a look. So here's X1, X2, X3. So here's U, V, W. So what's interesting is we started at 85 meters a second, but actually we lost some speed. Then we increased, we gained some speed all the way up to, geez, 135-ish. What is this? Oh, come on, flash up. There we, it keeps popping up and down when I hover over. Yeah, 136 meters per second. And it looks like it was stabilizing. There's no motion in the lateral directional states, which kind of makes sense, right? We started out with the aircraft only having longitudinal motion, so there's no W component, and there's no P, and there's no R, and there's no phi and no psi, which again makes sense. So again, it looks like the vehicle started slow and it did a little bit of oscillations, and it looks like it's about to probably come to hopefully to steady state. So for example, if we ran this thing longer, so for example, let's come back to our Matlab script. Let's run this instead of 60 seconds. Maybe let's triple the time. Let's go for 3 minutes of simulation and run this again. And hopefully we'll see what happens now. And again, I'll pull the state trace over. And yeah, this looks good. So it looks like at that throttle setting, it looks like the vehicle will eventually come to steady state here, around 120 meters a second. And yeah, this is very interesting, right? Now, what makes this kind of cool is we can now go ahead and start modifying this to simulate different environments. So maybe the first thing we should do is, to make this perfectly clear, let's make a subsystem out of this. So remember, all these blocks, this was the aircraft. So I'm going to select them all, right click, and then let's go ahead and create a subsystem. So this is basically the nonlinear 6 degree of freedom RCAM aircraft plant model, right? So you stick in some control surface deflections, and out comes the state. So now we can start playing some games. So for example, let's add like maybe an aileron pulse and see what happens. So what I mean by that is, tell you what, let's just do this quickly. This should be pretty easy and kind of fun. Let's go ahead and break this line here. Let's make a summing block, and we will have the U coming in here, and then let's maybe make some small delta U. I'm going to make this, whoops, I want actually like a step. Let's grab a step real fast. That should be under sources, and let's grab a step. And I don't know, let's make a step at 30 seconds. How about? So step of 30 seconds. Let's step to maybe like a 5 degree aileron, and then let's hold that for just 2 seconds. So maybe 30 plus, so 32 seconds, and then we'll go to -5 degrees. And if we now add those together, okay, that should be a pulse in aileron. And now we don't want to pulse anything else. So let me go ahead and get a mux here. We'll have 5 inputs, and what we'll do is, here's the pulse in aileron, and then the pulse in all the other channels. Let's just make them a whole bunch of zeros. So grab a constant, put a 0, and we're going to basically do something like this. Just put zeros into all these. Whoops. Come on, 0, 0, 0, 0. Okay, and connect these up. Okay, so this signal coming out of this thing, let's maybe turn this into a subsystem. This is like a delta U. Right? So if I hook this in, what we should be doing now is we're going to now fly along, in the longitudinal motion for just 30 seconds, and then at 30 seconds, we are going to crank the ailerons to 5 degrees, hold them for 2 seconds, and then bring them back. Let's see what this does to the simulation now. So if I, again, hook all this up, hit save, and now we can come back to our script and rerun this puppy, and give it a second, and let's go ahead and pull over the controls first. So here's our plot of all the controls. So as you can see, we're flying along for 30 seconds, and then we pulse the ailerons, a 5 degree aileron deflection for 2 seconds, and then we bring them back to 0. Okay. Now what's interesting about this is, if you look at the state trace information, again, there's no lateral directional motion for 30 seconds, but then after you kick the aileron, look at this. You start inducing some sideways velocity. You start inducing a rate. That's exactly what the ailerons are supposed to do, right? They induce a roll rate. Therefore, it also induces a yaw rate, kind of as a secondary after effect. And look at this. This is interesting. So luckily for us, it looks like even with this aileron kick, the system becomes stable and it stabilizes out. However, look at this. It stabilizes, and now it's no longer heading due north any longer, right? Psi is moved to this, almost -0.3 radians. So this is really interesting. There's a lot of interesting behavior now in this model that we're going to explore later. But long story short, at this point, we've set up a pretty good representation of an aircraft here in this block. So, maybe what we should do right now is revisit that discussion of the limits and the saturation. All right, so here's the issue with the way the limitations and the saturation on the control vector is currently being implemented. Let's say you wanted to do something like simulate an engine out or something like that. So an engine out would be, let's come back to our defined constants. We could maybe say, let's kill engine 1. So 0 control input. So I want to basically pretend like engine 1 provides no thrust and no force, no moment on the vehicle. So I could do this. However, the problem right now is if we trace that signal in the RCAM model, in our Simulink model, right? So coming out of this, U4 is 0. U4 is still 0. U4 is 0. Coming into everything, U4 is 0. U4 is still 0. Now coming into the interpreted Matlab function, we're going to pass into here, right? U4 as 0. So now we got to come over to RCAM model. So here's our RCAM model. right? Down here, U4 is still 0. So this thing right here on line 18, that's going to be 0, right? Now the problem is it's 0 here, which is good for our engine out. But however, when you come down here to the section where we introduce control limits and saturation, right here, we're going to trigger this statement, right? So we're going to land here on line 98, and U4 is not going to be set to 0. U4 will go to minimum. So basically, in this implementation, there's no way for us to shut off the force or the throttle to one of these engines completely. And I think it's a little bit insidious in the sense that this saturation limit is buried all the way inside the RCAM_model.m. I mean, as long as you're aware of it, maybe that's fine. So what I suggest instead is instead of having these limitations or these control vector saturations buried inside the RCAM model.m function, maybe what we can do here is actually, let's just copy all of this code, okay, which is our saturations. I will just copy this, and maybe let's comment this out inside the model here. So I will comment this out, comment, okay, so now RCAM_model.m is not doing any of the saturation. Instead, what we could do is let's paste some of this code into our initialized constants. So in here, where we're defining all the constants, maybe I'll put another little small subsection where we're going to say define minimum/maximum control values. So I'll paste some of that in here. What I want to keep is the top stuff. I don't want to do any of this. All this if statements, right? This was how we were trying to enforce those upper and lower limits. So I'm going to delete all that. All I care about is I want to keep these definitions of what is the maximum and what are the minimum values of all of these channels U1, 2, 3, 4, 5. Okay? So if I do this and now come over to the Simulink model, what you can do is inside here on the U signal, what I can do is let's go ahead and first break this out. So I'm going to grab a demux, 5-element demux, okay? Let's do it like such. And maybe I will disconnect this temporarily, hook this up like so. And now what I'm going to do is let me blow this up so we have a little more real estate to work with. I'll move this up, okay? Okay, what I'm going to do is I would like to now implement saturation here. So I'm going to say saturation. I'm going to grab a saturation block. Saturation does exactly what I want to. Here, this is going to be U1. And what I want coming out of this guy is basically U1 saturated, which is respecting and obeying those limits. So now if I come into here, I can say this upper and lower limit. What did we actually call this? Let's come back to the script here. U1 min and U1 max. So what I can do is in this saturation block, the lower limit is U1 min, the upper limit is U1 max, right? So that will implement saturation. Let's do the same thing for all these other channels, right? And we'll hook them up, and then all we have to do is change these values in here to the appropriate ones. So now this is U2 and U2, and then this guy is U3. Oops, come on. Jeez. U3 and U3, and then finally, here's the engines, right? This is now U4 and U4, and then finally, we're at our last one, U5 and U5. Okay, and now let's mux these all up together. And again, this is now 5 elements. And if we hook this up, hopefully what we've got now is if we, again, select all these, let's get them all connected. Come on. Don't tell me it's not going to be smart enough about that. All right, fine. We're going to have to manually hook all these up. But I think you get the picture at this point. And I guess these are not U1 sats anymore, right? This is U2 saturated, U3 saturated, U4 saturated, and U5 saturated. So now, if we do something like this and hook this up, right, we've basically moved the saturation and the limiting out of the RCAM_model.m, and we've done it explicitly here where it's very easy to see what's going on. And more importantly, what we can do now is in our initialization script, we can change these to appropriate values. So example, if we wanted to be able to shut off U4 completely, we need to be able to change this minimum here to, instead of being 0.5, this needs to be able to drop all the way down to 0, right? So now we're allowing the engine 4 to be completely shut off so that when we go ahead and put in this value, it will turn itself off. So now if I run this simulation again, well, I don't anticipate this going well because we're flying for 3 minutes with one engine. Well, it ran. Let's go ahead and take a look at the results. So here you go. Here's our aileron pulse. And then look at this here. U4 is sitting here at exactly 0, right? So the engine 4 is completely off. And hopefully what we've done properly is since we handled the saturations properly, the force from the engine that's actually acting on the vehicle is actually 0. And as you can see, we're in big trouble here when that happens. Look, this is like, yeah, stuff is going kind of wrong. Although, surprisingly, this is not too horribly wrong. It does almost look like we actually end up at a steady state. Wow, so I'm actually shocked. I guess at this low throttle setting, it looks like we are actually flying stably. Although, if you look at psi, it looks like we're just in a turn, right? We are in a counterclockwise westerly turning, we're basically going around in circles at this point. But again, that makes sense. We've got one engine on and one engine off. So this is great, I think. I think we're at a really good spot. Maybe what we should do is I will whet your appetite a little bit by, looking at this graph, we're trying to interpret what is going on, right? What is the aircraft doing? It's a little hard, at least in my opinion, to just stare at state traces and try to understand what the vehicle is doing. So what we're going to look at in a future video is how can we take this Simulink model that we built with our aircraft and maybe instead of just sending data out to be plotted, can we send that out to some kind of a visualization package to visualize, like a flight simulator, to visualize what the vehicle is doing and how it's responding. And even further down the road, if instead of just having inputs right here of just constants or doublets or pulses or sine waves or things like that, wouldn't it be awesome if we could just put in like a read from a joystick or something like that, so we could actually have a pilot hopefully fly the vehicle by inputting joystick commands. Our system, the simulation, the flight simulator that we develop will be doing all of the engineering calculations and computing the states, and then we will send that information out to a flight simulator to visualize it. So really, if you think about this, we are going to be building our own honest-to-goodness, full nonlinear 6 degree of freedom RCAM simulator / flight simulator, right? So this is going to be pretty fun coming on down the pike. So stick around. I'm very excited for that. So with that being said, I think this is a good spot to leave it. I hope you enjoyed the discussion today, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll down a little ways and click on that subscribe button, it really does help me continue making these videos. Please also let me know what you think about this video or any other videos down in the comments. I really would love to hear from you. With that being said, I hope to catch you at one of these future discussions, and until then, I think I'll sign off. So, talk to you later. Bye.